Welcome to this video on differentiation. This video will cover key concepts, including gradient calculations, derivatives, and various applications in calculus.
Let's start by looking at gradients and curves. While the gradient of a straight line is constant, the gradient of a curve changes continually. At any specific point, the gradient of the curve is equal to the gradient of the tangent at that point. As you can see, the gradient of the tangent line provides the gradient of the curve at that exact location, whether at point A or point B. To find the gradient at any point on a curve, we must modify the standard gradient formula. For a function y equals f of x, we take our point and a second very close point, then calculate the gradient between them. This approach gives an approximation. To improve this, we make the distance between the 2 points, denoted as h, smaller, bringing the points closer together. By making h even smaller, the points become even closer together, refining our approximation of the true gradient. The process of finding this gradient or rate of change is called differentiating, or finding the derivative. If the equation of the curve is f of x, the derivative is written as f prime of x. There is a simple rule to find this derivative from the original function. The rule for differentiating is straightforward. Multiply by the power, then reduce the power by 1. If f of x equals a times x to the power of n, then the derivative is a times n times x to the power of n minus 1. To succeed with differentiation, it is very important that you are comfortable working with indices rules, as summarized here. Let's look at special cases. For a straight line function where f of x equals ax, the derivative is simply a. This matches what we know about the gradient of a linear equation. For a horizontal line where f of x equals a constant, the derivative is 0, which makes sense as horizontal lines have a gradient of 0. Here is a summary of various differentiation techniques, showing how different functions and their derivatives are related through these rules. Let's practice. Differentiate the expression 4x squared minus 3x plus 7. Applying our rule, we get 8x minus 3. Finally, differentiate y equals 2x cubed minus 7x squared plus 4x plus 4. The resulting derivative is 6x squared minus 14x plus 4. Let's review these calculus examples. First, differentiate the function a of x equals 240x minus 16 over 3 times x squared. The derivative is 240 minus 32 over 3 times x. In this example, for a curve with equation f of x equals 3x to the power of 4, the gradient formula is 12x cubed. When x is 2, the gradient is 96. For 3x squared, the gradient is 6x, and at x equals minus 4, the gradient is minus 24. For the function g of x equals 5x to the power of 4 minus 4x to the power of 5, the derivative g prime of x is 20x cubed minus 20x to the power of 4. Evaluating this at x equals 2 results in minus 160. For h of x equals 5x squared minus 3x plus 19, the derivative is 10x minus 3, yielding minus 43 at x equals minus 4. For k of x equals 5x to the power of 4 minus 2x cubed plus 19x minus 8, the derivative at x equals 10 is 19,419. To find points on the curve f of x equals x cubed minus 3x squared plus 2x plus 7, where the gradient is 2, set the derivative to 2. Solving this gives x equals 0 and x equals 2. The corresponding points are 0, 7, and 2, 7. Moving to further examples, this slide provides additional practice on differentiating specific functions involving polynomials, reinforcing the rules we have covered. Here we see differentiation applied to functions that can be written in a straight line form or simplified before applying the derivative rules. Continuing with these practice problems, we apply the standard differentiation rules to various expressions to further build your confidence. This section introduces slightly more complex functions, requiring you to simplify or use the chain rule before differentiating. More practice with differentiation rules is essential. Ensure you correctly identify the terms in the expression before calculating the derivative. These examples demonstrate how to handle functions that are not immediately in the standard power form, requiring simplification first. Consistency is key in calculus. Applying the same differentiation rules to these remaining expressions will solidify your understanding. When dealing with brackets, always expand them before you differentiate. For h of x equals 2x times x plus 3 times x minus 3, First, simplify to 2x cubed minus 18x, then the derivative is 6x squared minus 18. Here is another example of multiplying out expressions before differentiating. This standard approach helps avoid errors when handling complex functions. Finally, we conclude our revision by practicing the steps of multiplying out and differentiating for these final expressions. Let's explore some more advanced differentiation techniques. When dealing with complex expressions, simplifying the form by multiplying out brackets is an essential step before you begin to differentiate. This approach is particularly useful when you encounter expressions that are not in a simple polynomial form. Always remember to multiply out first to ensure the differentiation process is straightforward. In some cases, you may need to multiply out, simplify the terms, and then differentiate to arrive at the correct final expression. By methodically following these steps, multiplying out and then differentiating, you can manage more complex polynomial structures effectively. Now, let's look at dealing with fractions. By reversing the previous rules, we can apply a specific method to differentiate functions that contain fractional terms. For example, if you have f of x equals 3x cubed minus x plus 2 divided by x squared, you can rewrite the fraction into a form with negative indices, making it much easier to differentiate. When you encounter these types of problems, the best strategy is to split the fraction up, rewrite each term in a linear format using negative indices, and then apply the standard derivative rules. Another useful notation is the Leibniz notation. While you are likely familiar with f prime of x, writing the derivative as dy over dx is a standard alternative, especially when y is expressed directly in terms of x. Let's apply this to an example. If a curve has the equation y equals 5x cubed minus 4x squared plus 7, the gradient is found by calculating dy over dx, which is 15x squared minus 8x. Calculus also has applications in physics. For example, Newton's second law of motion can be analyzed using differentiation to find velocity, which is the derivative of distance with respect to time. Next, we will look at the equation of tangents. At any given point A on a curve, the gradient of the tangent line is equal to the gradient of the curve at that specific point. To find the equation of a tangent line, you first need the point of contact and the gradient at that point. Once you have those, you can use the formula y minus b equals m times x minus a. For example, to find the tangent for y equals x cubed minus 2x plus 1 at x equals negative 1, you first calculate the coordinate point and the gradient, then apply the linear equation formula. In this next example involving fractions, the process remains the same. Find the point on the curve, find the gradient by differentiating, and determine the tangent equation. Once you have the tangent equation, you can also determine where it cuts the axes by setting x to 0 for the y-intercept and y to 0 for the x-intercept.